Everyone, welcome back to the channel. Today we are deep diving in one of the most elegant and educational implementation of GPT model ever created. That's nanoGPT by Andrej Karpathy and his team. So this is going to be a comprehensive technical breakdown, so grab your favorite beverage and let's get started. At first, we will be looking at the model.py file in the repository. This is a masterpiece of clean educational code that implements the entire GPT architecture in 300 lines. What makes this special is complete GPT implementation in just a single file, that direct mapping from research paper to code. Now, let's look into the deeper. Its first layer is layer normalization. It is like a quality control check for neural networks. Imagine you are cooking and need to keep ingredients at consistent temperature. Layer normalization does this for neural network values. Why this custom implementation is necessary? So PyTorch build in layer norm always includes biases, but sometimes we want to turn it off for efficiency reasons. So it normalizes values to have mean equals to 0 and variance equals to 1, then applies learnable scales, that's weight and the shift. Now comes the attention mechanism. This is the revolutionary part that made GPT possible. Casual self-attention. Think of attention like a query, key and value, where query is what I'm looking for, key is what information do I have, and value is what is the actual content. Imagine you are in a library. Your query is I need information about machine learning. So each book title is a key. The actual content inside the book is the values. Attention calculates which book meets your query, then retrieves their content. That's the values. Now, the multi-hand attention explanation. Instead of one librarian, that's the attention head, we have multiple librarians. Each focuses on different aspects. One might focus on grammar, the other on meanings, and maybe another on context. Why this is necessary? Different heads can learn different pages, different types of relationships. There comes the magic calculations, in which let's break down some mathematical calculation here. Here you can see this function calculates the similarity between queries and key. This one scales to prevent huge number and keeps the gradient stable. Now, the mask fill, it's a casual masking where words can only look at previous words, not the future ones. Which means that predicting the next word, you can't check the looking at future words. It's like taking a test where you can only see previous questions, not the upcoming ones. What this NMLP blocks does, it seems a bit new. So what this doing is think of it as a thinking space. Input comes in dimension, gets expanded to a larger space that's like 3072 dimension where the model can think more complexity. The GELU activation, it's like ReLU but smoother, helps the model learn more linear patterns. Then the contrast breaks the original sizes, and why this 4x expansion is necessary. So explicitly found to work well with given models more capacity to process information. Now, what this block does, this is a transformer block, which does the magic of residual connections. As you can see, it's like x equals to x plus self attention, which means it takes what we have just before plus what attention learned. So why it is necessary? It prevents the vanishing gradient problem, allows very deep networks to train. Now, what's the analogy behind it? Like revising an essay, you keep the original text and add improvements rather than starting from scratch. So you add on in it. Notice self.ln underscore 1. It happens before attention, not after. This is called prenorm, found to be more stable for training purposes. Now, what this GPT config does? It has some numerical values. So let's understand these numbers. GPT-2 small has 12 layers, 12 heads, and 768 embeddings. That results into 124 million parameters. Vocab size is set to 50304. Oh, what this weird number is? It's 50257 for GPT-2 vocab, but we rounded it to the nearest multiple of 62 for GPU efficiency. Now, the block size is set to 1024, in which the model can look back at most 1024 tokens. Every machine learning enthusiast is known to be like why it is set to 1024 or why it's a multiple of 64, 24 or 12. Now, let's understand the complete GPT model. This class GPT breaks down the components. This token embedding converts the tokens into densest vector. Each vector or subverts can into a unique 768 dimensional vector. Think of it as like a given search word, a DNA sequence that captures its meaning. Now this positional embeddings tells the model where each token appears in the sequence. Like it's a sequential position of the token where in your line. Position 0, position 1, position 2, etc. etc. Each gets their own learned vector. Why it is needed actually? But like when you're reading this essay and you just mix match the words, so it makes no sense. So attention doesn't inherently know the order. This adds position information. Now comes the forward passes. It's a forward pass in which we have to convert tokens to embedding, like hello to 123 or something else, then add position information, then pass through 12 transformer blocks, each one refines the representation, then final normalization, which cleans up the values, then converts back into the vocabulary, like an encoder decoder. That probability is over 50k possible networks. Now, this self-attention.wts.weight, this is the input embedding matrix in which the same as the output propagation matrix. So why it is necessary? It saves parameter and often improves performances. What's the intuition behind it? It's like if word cat has something vector like 1, 2, 3, then word predicting character, the model should output 1, 2, 3 only. Why? Why this weights initialization matters? Start with small random values so gradients can flow properly, and the standardization is set to 0.02, not too big because it would cause exploding gradients, or too small would cause vanishing gradient problems. Everyone has known this vanishing gradient and exploding gradient problems, and everyone wants to improve it. So this is why standardization is set to 0.02. So let's come to some of the advanced features in it. Let's loading the pre-trained models. This is one of the most sophisticated part of the code. Let me break down and step by step. So what's happening here is this class method, which means you can call GPT pre-trained GPT-2 model without creating an instance first. Only accepts official GPT-2 variants and overrides restrictions. You can only change dropout weight, nothing else. It prevents breaking the pre-trained models. Now comes the Hugging Face import, using this transformer library to download from OpenAI's official weights. What this configuration mapping is, as you can see, they are GPT-2, GPT-2 medium, large. So understanding the scaling, like GPT-2, it's having 12 layers, 12 heads, and 768 dimensions, and more like this all these models have. The key insight from this is, notice how they scale different dimensionalities, layers, heads, embedding size, each have their richer representations. Why these are fourths? Like as you can see, vocab size is treated as 50257. This is the GPT-2 exact vocabulary size. Block size is set to 1024 and bias is set to true, which means GPT-2 was trained with bias systems, removing from changes the computation. Now let's understand the step-by-step processes of this weight transfer process. Create empty nanoGPT model with random weights but correct architecture. Then download the Hugging Face model, guess the OpenAI trained weights, and get start dictionary. This contains all the parameter tensions, fills like all the non-parameters, remove attention, bias mask, and the tricky part, that's the weight transformation, here comes. So it converts the 1D into linear problem. OpenAI implementation uses convolutional layer 1D convolutional layer for historical reasons, and nanoGPT implementation is it uses standard linear layers that's simpler and more commutable. The fix is transpose the weight matrices while copying. Think of it as like a matrix multiplication A into B, where A is M into N and B is N into P. So if OpenAI stores B, that's P into N, and we expect N into P. The solution is transpose the B matrix with copying B dot transpose and convert into P into N, convert into it into N into P from P into N. Now, what this configure optimizer method does? This method sets up the optimizer with some very clear parameter groundings. Getting all trainable parameters returns pair for every weight loss or weight in biases, only include parameters that needs gradients, like excludes all frozen layers. This is done by these things. And now comes the small parameters grouping. Why this is metering? So 2D parameter matrix, attention weights, MLP weights, embeddings, and apply all these weight decay. Now 1D parameters does, these are the vectors, so it stores biases, layers, norms, parameters, and there is no weight decay. Weight decay intuition is like, its purpose is preventing overfitting by penalizing the large weights. And why not on biases? Biases are scalars that shift outputs, weight decay, and doesn't help here. But you have a question like, why not we used it in the layer normalization? So these parameters control normalization, not representation capacity. Now, one of its advanced optimization features are like these numbers, number of decay parameters, number of no decay parameters. It is infused with Atom W optimizer. So it's a regular Atom, maybe fused, maybe performance gain. It's used for like 10 to 20% speed up on modern GPUs, and when available, PyTorch for like CUDA purposes. Now, this model performance analyzes the estimate MFU method. This method estimates how efficiently we are using our GPU. Let's understand this calculation. So, the formula 6 into n, it's a forward pass through all parameters, that's 3n, plus back forward pass, that's 3n. So 12 into L into H into Q into T, these are the additional operations for attention computations, where L is the layers, H is the heads, Q is the head dimension, and T is the sequence length. So it is trained on A100 performance context, that's peak theoretical 312 TF flops, trillion flops like per seconds. So why this MFU is important? It is cost efficient and it identifies the bottlenecks. It is optimizing the guidance, helps decides if you need bigger models or bigger optimization as such. Now, this generate methods. This is where the magic happens, turning a trained model into a text generation model. For this setup, you need a torch, no gradient. It disables the gradient computation, saves memory, and speed up the inference time. And the model evolution, it should be called before this to disable the dropout and set batch normalization model. Now this comes, and all these things. The temperature works with like temperature if 0.1, then its logics makes different bigger, more deterministic, and temperature is if set to 1, then temperature divided by 1.0 keeps original probabilities, and if temperature set to 2, it makes differences smaller but more random. Examples are shown here, and this and this. There is a sampling process in it also, so which uses the top key elements. The sampling process is like convert the probabilities. Softmax ensures they sum to 1, and the sample from distribution, which is a multi-model, randomly picks based on probabilities, and then append the chosen token to continue. Why this sampling is used? Why not greedy? So greedy always picks the highest, boring repetitive text, but sampling is more creative, adds randomness, variance, and human-like text. So control sampling, which is like temperature plus top key elements, it is balanced between coherent and creativity levels. Now comes embedding part. Why exclude position embedding? So standard in reports and papers, it is standard. The position embedding fixed to context length and not core memory of the model capacity. The token embedding kept because they are shared with output layers, whether it is weight or time. Now let's come to the crop block size method. What it does is, it is a use case example. Let's take a use case example. So it loads the GPT-2 trained model with 1024 context values, and what shorter context, like example for 512 or like 256 for faster inference. The solution is like crop position embedding and attention task. It reduces the memory, so it is faster in inferencing. So like how everything is interconnected to everything. Let me explain how these components work together. At first, the model creation of workflow. The model creation workflow works like, then the training setup flow is done, then inference flow is done, as you can see here, then complete data is flowed. This is all from it, and what I would give as an insights for beginner, why this architecture is really working, because self-attention, it lets every word talk to every single word, every other word. Residual connections prevents training problems in deep networks, and the layer normalization keeps the value in good ranges for stable training, and the position embedding gives the model a sense of word order. Now, the memory versus computation rate words, that comes in every model. So the larger the model, more parameters, more memory, but potentially better quality. The longer sequences is equals to more context and equals to quadratic memory growth in attention. What's the batch size here? Larger the batch size, better GPU utilization, but more memory. So we have to keep all these things in mind and train our GPT-2 model. What's the beauty of this implementation is, I love it, like it's done is 300 lines, the complete GPT implementation. No hidden complexity, every component is visible and modifiable. For educational purposes, like direct mapping from research papers to code, production ready and can actually train comprehensive models. So in conclusion, I would say the model.py file is like nanoGPT is like a masterpiece of clean educational code. So this guides cover the complete model.py file from nanoGPT, and for training, data pre-processing and sampling, sees the accompanying guides for like all these things. As the video is quite long, so I will break it to it and understand the next context in the next part. Thank you.